Good morning, ladies and gentlemen. It is a cold day here in North Carolina, but that is okay because today we are going to be building a blockchain from scratch in Python. So if you want to follow along with the source code here, you can go visit my GitHub. There is a link to that in the description. Feel free to follow my account while you're there and leave a little star on the sketchbook. But what we want to do is switch to the Python blockchain branch here. I have a lot of different sketches that I do. And if you want to follow up with what I'm doing right now here in the stream, then this is the branch that you want to look at. Okay, so at the end of this video, what we are hopefully going to have is a functional blockchain. And what I mean by functional is that you would be able to use this for maybe a small-scale game with friends, or maybe some small application that you want to use. It's not going to be quite robust enough for a industrial application, and we'll talk about why more towards the end of the video. But before we can actually build something to that scale, we want to have an understanding of a blockchain in its totality, to some degree at least. So I want this video to be a reference point for everybody so that we all kind of know what I'm talking about when I discuss blockchains. So without further ado, let us begin talking about the blockchain. Okay, so I have my sketchbook here, and it is just an empty Python file. Now, I want to show you that I do have in this directory a virtual environment, and I'm going to switch to that environment here in the terminal. Let's make the text a little bigger for you guys. So I'm going to say source env/bin/activate. I thought I spelled that right. Off to a great start. Oh, perhaps I didn't create. Okay, I guess I did not create the virtual environment yet. So we can go ahead and do that right now. Perfect opportunity to learn. Hooray. So what we're going to do is use that environment bin. Let us go ahead and just go inside and let's just delete that. And let us create a virtual environment for Python for us to work in. Now, we're not actually going to use any third-party libraries in this process, but it's just a good habit to kind of work in virtual environments just in case you do. So what I'm going to do is notice that I already have my env folder created. So I'm going to do python 3-m venv and then env for the folder where I want to create this. It'll take a second to run. And there we go. So now I can say source env/bin/activate. There we go. Now we have our Python virtual environment. So what this does is essentially create a separate installation of Python on my machine. And it allows me to install any third-party libraries I want and essentially mess around with things however I like and create a separate container for Python. It keeps things separate so I don't contaminate other things on the system. Anyway, we have our virtual environment, so let's begin talking about how we are going to build this into a blockchain. This is going to kind of hinge on importing this hashlib library. And before we can discuss blockchain, we kind of need to understand the fundamental element of blockchain, and that is the cryptographic hash, excuse me. And a hash is kind of the key that makes blockchain possible. So we want to have a good understanding of what hashes are before we begin. And in short, a cryptographic hash is sort of, if you think of a cipher that you would write with someone that you know, you sort of scramble a message, you send it to them, and then they have some sort of key that can unscramble it. Well, a hash is sort of a one-way cipher. So you put something into it, it will scramble it, and give you something out that isn't meant to go back to what it originally was. And the key features are that it is seemingly random. So when I put in one thing into the algorithm, it will give me a result that isn't really predictable. but every time I put that thing into the algorithm, I will get the same result. I can demonstrate this. So I'm going to do this here in the terminal because it's a little bit quicker, and we'll move back to Xcode in a moment. So I'm just going to open Python. I'm going to import hashlib, and I'm going to say h equals hashlib dot SHA-256. Now, SHA-256 is the secure hashing algorithm using 256 bits. And it was developed by the NSA, and it's actually not out of date yet, but it's soon going to be replaced by SHA-512. But we're just going to use 256 for now because it'll be a little bit shorter. You'll see what the result of this is in a moment. So we're going to create an instance of a SHA-256 object from hashlib. Just to be clear, there are other types of hashing algorithms out there. SHA-256, I believe, is used in Bitcoin, either that or SHA-512. I don't remember off the top of my head. But anyway, we're going to create an instance of a SHA-256 object, and then we're going to say h.update, and updating a hash is essentially using the cipher. So they are going to have a particular thing that you do with the data that you send in, and it deals in bytes. So you're going to send in some stream of bytes. It is going to manipulate those bytes in some way, and then it's going to give you an output. And let's just go ahead and run it so you can see what this looks like. So I'm going to send it the character A, but I need to encode that as bytes. So I need to say encode, and I'm going to use UTF-8. And now I can say h.hex digest. And there is our SHA-256 hash. Okay, before we go any further, let me just say that if you are interested in learning how the SHA-256 algorithm works kind of at a more fundamental level, then I would recommend this video here by learnmeabitcoin. Good name. Anyway, so learnmeabitcoin made this video. I actually have a link to it in the description, and it is just a fantastic visualization of how SHA-256 works. And I actually have it in my mind that I would like to build my own function for doing this manipulation, so I really understand it. But that's going to be for another time. So if you want to know nitty-gritty how SHA-256 works, I recommend this video, and I actually will also recommend my own channel because I want to do this sort of thing too. Anyway, we have our hash here, and what's important to note is that when I put the letter A into this hash, nobody really expects this as the output. And what's important is that if I do this exact same thing again, I will get exactly the same result every time. So I can create a new instance of a hash object. I can then update it with my character encoded as UTF-8 bytes, and then I can get the hex digest, and it will give me exactly the same result. And what this result is essentially they are doing a 256-bit chunk of whatever you send in. And you just take these 256-bit chunks, you perform the manipulations that are demonstrated in Learn Me a Bitcoin's video, and at the end, those 256 bits will end up representing a number in hexadecimal. And so our output as a hex digest is a hexadecimal number. And if we copy this, and I can pull it up, I'm meant to have all my tabs already open. So we can convert that hex to a decimal. And we can see that it is an absurdly large number. And every time I put some data into a hash, it will give me a pretty much unique output. And if I change anything about that data, it will give me a totally different output. So if I put in, let's do h equals that, and then we'll encode, instead of just A, let's say A, B, C, D, E, F, G. And now we can say the hex digest of this And now let's change a single character in that. And instead of saying EFG, let's say EFH. And let's get our hex digest. You can see the hex is completely different. And that's really the key. This being represented as a number is really a representation of how many different possible hashes. Oh, I see some people in the chat. Hello to Camel Trader. I think I remember you from GitHub, unless you just have a similar name. Andrew Yu, hello to you as well. I don't recognize your name, but you are absolutely welcome. And Cheryl, your name seems kind of familiar, but I don't remember from where. Good morning to you. Anyway, so the fact that this is such an absurdly large number is due to the fact that the SHA-256 algorithm has 2 to the 256th power possible outputs. So we can do 2 to the 256. It has that many possible outputs. That's an absurdly large number. So any data that we put in is pretty much going to give us a unique hash. And if you change anything about that data, you change the hash entirely. Okay, so that is kind of our introduction to hashes. And so how does this relate to a blockchain? And how do we make a blockchain out of these raw hashes? Well, the key is going to be in the fact that they preserve the data that they have hashed. You know that the data has remained the same. So let's go in and start working on our blockchain. And what we'll kind of want to do is think about this as a linked list. So if you've never used a linked list before, essentially what you would do is something like this. I would create a class. Let's make the text a little bigger for you guys. So we would make a class. I would call it node. And let's just say our node class will define init, pass itself. And we'll say data equals 5. It doesn't matter. And then next equals none. Forget how they do it in Python. Okay, so next equals none. And what we would do essentially is whenever we add the next item to our linked list, next would become that item. And then that item's next would become the subsequent item. And so essentially we create this list of objects by sort of embedding them one within the other. And that's what we're going to do in the blockchain. We are going to essentially embed one block in another using the hash. And we can use the hash to guarantee that the chain has not been manipulated. And that's really the goal here. So I suppose the best way to approach this is to sort of put our hashes to the side for a moment. Just take it that we know what our hashes are. We're going to need them in a little bit, but let's talk about how we are going to structure a block for a moment. So Brooks Burris, will you be trying to build a blockchain in C after this once you learn the fundamentals? Yes, absolutely. So the point of this video is actually for the viewers. So I want to make sure that everybody has a reference point to what a blockchain kind of is fundamentally. That way, when I'm talking about some of these low-level concepts about contiguous memory blocks and sending it across sockets, that I can take for granted the things that I want to take for granted. So this video is the prerequisite to us building things in C and allowing me to kind of assume that you know things because I can always reference this video. Okay, so let's talk about the structure of what our block is going to look like and what the chain is going to look like. So to do this, let's create a simple class. And I can do this in the main file, but I'm a clean freak. So let's go ahead and create a new file for this class. And I'm going to call it block. Oh, we should call it block.py. Okay. So we're going to have a class. I'm going to close that and reopen it. Sorry. Not recognizing that it's Python, I don't think. Let me recreate that file. That didn't go well. Sorry about that. There we go. Okay, so our class block. We'll just create an init. In case you aren't aware, the init function is what runs by hello, Mr. Gamer. The init function is what runs by default as soon as you instantiate the class. So this is just as soon as I create a actual instance of my block, then this function will run. But anyway, we're going to have a few variables here. So we're going to have self, and for now, let's just have a few necessary ones. And you know what? Before we actually even build this into a block, let me show you what we're going to need kind of fundamentally. Okay, let's take a different approach here. So we saw that our hex digest is in fact a number. So what we can do is apply a difficulty to our blockchain and say, more or less arbitrarily, we will only accept blocks whose hash is below a certain number. So if the maximum possible hash in SHA-256 is 2 to the 256 power, we can say that we are only going to accept a hash that has a value that is 2 to the 256 minus our difficulty. So let's say 10. So it has to be less than that. So let's see. We can convert our hex digest into an integer. So we can say int h.hexdigest. And we have to specify that this is in base 16. Okay? And we can say, is that number less than 2 to the 256 minus 10? It is not. So this hash would not pass our difficulty requirement. Mr. Gamer, are you trying to create the hashlib library for C? No, not yet. I have it in my mind that I will be creating a SHA-250. Actually, I'll be doing SHA-512, but I'll be doing a SHA-512 algorithm of my own, but I'm not going to recreate it. I'm just doing a baseline blockchain here. Anyway, so we can see that our hex digest here is not, in fact, less than 2 to the 256 minus 10. So this would not satisfy our difficulty requirement. So how would we make it satisfy our difficulty requirement? Well, what we're going to do is add another arbitrary piece of data that we can manipulate. And this piece of data will let us test different hashes. So let's say let's do it like this. So I'm going to say I equals 0. Now, h equals hashlib dot SHA-256 and h dot update let's go. You have to convert it to a string and then encode it as UTF-8 bytes. We have to do it that way because we need to send it bytes, and I is currently an integer, which is an object in Python, which is not really ready as bytes. And Jim, hello, how are you? Okay, so we're going to update it with the current value of I, which is 0. So if we do this, then we can say, we can do the same test. So let's just, where is it? There it is, okay. Again, it's false. It's the hash of 0 is not less than our difficulty requirement. So we can say, while this is true, while that, we're going to create a loop. And we're going to say I plus equals 1. And then we're going to say h equals, well, no, we're just going to say h dot update string I dot encode f-8. We'll update the hash, and we will just keep doing that repeatedly until our hex digest is less than our difficulty requirement. So if I run this loop, pretty quick actually, and now I can just say h.hex. Well, let's just go ahead and run the test condition just to see if it's true. False. Oh, I did the while statement wrong. Silly mistakes. They cost you. Okay, so let's bring that back up. Let's fix this. Okay. H dot run our test condition. True. Okay, so h dot hex digest. And what's important to note about this hex digest is that it's actually kind of immediately recognizable as successful because of these leading zeros. We can see that these leading zeros, it's the leftmost bit is the most significant bit here. And we can see that these most significant bits are 0. And that pretty much tells us right off the bat that this is less than 2 to the 256 minus 10. So that's a good indicator that we are on the right track. Okay, so this is essentially how we are going to be mining our blockchain. Essentially, we are going to have whatever data we want, and then we're going to create a new section. And that new section is going to be some integer. And this blockchain is going to have some difficulty requirement. We're going to get that difficulty requirement, and then we're going to hash our data. And we're going to keep hashing it each time incrementing our arbitrary integer field by 1 until we get a hash that suits that difficulty requirement. Once we have that, we have successfully mined the block, and we are good to go, and we can move on to the next one. Okay, so let's actually create that as an object that we can visualize and stop working in this command line environment because it's actually a little bit difficult when you start making mistakes. So we have a block here, and this is just some abstract structure that is going to store all of those different things. So we have our data, and we'll just set this equal to data, which we assume the user is going to pass in. Now, we also want to set up a hash for this block. So we'll just say self.hash equals none. Okay, we're going to calculate that later, so let's not worry about that just yet. Okay, we have our data, and we're also going to need a nonce, and that is the number that is being incremented in order to generate the hash that suits our needs. So we're going to say self.nonce equals 0. We can just instantiate that to 0. And this is going to be all of the things that we need. But we should be careful here because this sort of hints at one of the ways that we are not going to be able to build something that is suitable outside of a entertainment or educational setting. So Python isn't really well suited for what we would need to do in a production environment here. And the reason for that is that when we want to, you remember over here when we would actually encode this as bytes? Well, we need to provide a way to send our data as bytes. And as some of you mentioned, usually on this channel, we work in C. So in C, that's actually kind of easy to do. And I've spent the last week working on how we are actually going to do that. But Python, it's going to be a lot more difficult. The easiest way is going to be this. We're going to define a string method. So def __str, and then we'll pass it self. Now, this is a default method. Just like how the init function runs whenever you create an instance of a block, the __ string function runs whenever you pass this object into a parameter that is being treated as a string. So if I say like print this object. In that circumstance, it's being treated as a string, so this function will run, and whatever I tell it to return will return as a string. So what I want to do is create a string, and I'm just going to have it do the hash, well, not the hash, let's just do data and the nonce. We can .format self.data, self.nonce. We're not going to put the hash in there because this is what we are using to hash it. So the act of calling this is going to most likely change the hash, so we're not going to put that in there. We are going to adjust this later though. So we have our small block object, and wondering if I want to incorporate the hash into this object itself. Yeah, okay. Here's what we'll do. We're going to create a function, and this function is going to essentially do what I was doing here. How we are going to mine it. We are going to pass itself in as a parameter as the data to be hashed, and we're just going to keep updating it. So that's what we need to do. But there's something really important that I almost forgot, and we need to see it. Okay, this is going to be super important. So we have found a value for I, this value for I, that supposedly, when we put it through the SHA-256 algorithm, we are going to get this hash. Remember that the same data going in is the same data coming out. That is how SHA-256 works. But that's not going to be the case here. Watch, if I create a new SHA-256 object, h.update, and I pass in that data, well, let's go ahead and pass in string I.encode date. Digest, not the same. Okay, so why would it not be the same? The reason is that in Python, these hash objects are cumulative. So every time I update it, it's not resetting it. It is just adding more to it. Remember that we have this sort of cipher pattern that we run, and we pass some data into it that gets kind of pushed through this cipher program that gives us some output at the end. And we can continue to pass more data into it as we go. Later on, we can take more and pass that in. And then we can take more and pass that in and just get a cumulative hash of all of what we put in there. And that's what we did in the while loop. See, here in the loop, we just update h each iteration. We don't create a new instance of h. So if we update h with all the numbers between 0 and 2629, then we will get this output. But we want something that gives us the output immediately. So let's recreate our while loop. So I'm going to clear this, and we can say while int, well, let's create a new instance. Okay, so h equals 256, I equals 0, h equals, well, h dot update, string of I dot encode UTF-8. Okay, so now while int h dot hex digest base 16, while that number greater than 2 to the 256 minus our difficulty requirement, we'll just set it to be 10. While it is greater than that, we are going to say I plus equals 1, and then we are going to reset our hash object. So h equals .256, and then h dot update string of I really need to stop working in this terminal environment. Dot encode UTF-8. Okay, I think that's right. Yes. Okay, there we go. So now I equals 286. Apparently, if we put 286 in, then that apparently solves it rather quickly. So what is our X digest? Remember that the output is random, so there's no guarantee that if we have an extremely high difficulty, that putting in a number like 2 won't give us the output we're looking for. There's no way to predict the output from the input, and that's what's so important about it. So the fact that it's 286, it's pretty much random. But anyway, so this number, every time we hash this number on its own, we will get this output. And that's what we're looking for. So we are going to create a function that is going to do this loop. Okay, we are going to go through this loop and mine our block, essentially get some difficulty requirement and find the hash that suits us. Okay, so that's where our string method is going to come in as well. So you'll see that in a moment. So def mine, we're going to pass it self, and let's pass it a difficulty. So we as the block, we are now blocks. Let me check my battery real quick. We're good. Okay, so we as blocks, we are now blocks. We don't know how difficult we are. We don't know how difficult the blockchain has decided we need to be in order to mine. So we are going to not make any assumptions there. And we are going to let that be passed in as a parameter here. Okay, so what we can do is create a hash. So self.hash equals, we're going to need to import hashlib here. So self.hash is going to equal SHA-256. And you know, we could skip that step if we did it up here. Instead of saying it's none, when we initialize it, we're just going to go ahead and create that. Now, down here, we'll be able to just enter our infinite loop, and that will make it easier. So, while the string of self, okay, that's an interesting thing. String of self. So self, remember, refers to the block object, our instance of the block, right? So we're going to pass self in here. And if we create a string out of that block object, it calls the string function. So the result of this is actually defined right here. Okay, so if we take that string and we encode it as UTF-8 bytes, we can then pass it in as the argument for our update. So we can say h.update. Well, we actually don't want to. We don't want to do that just yet. we actually just want to update it with the data as is. We don't want it in a while state. The reason is we want to kind of initialize that first hash. We want to get our first hash out there. And so we can say while the, not string, but int of h.hexdigest base 16 greater than 2 to the 256 minus difficulty. So while it is greater than that, we are going to actually increment the nonce. Plus equals 1. And then we can reset and rehash. So remember, we have to do both. We have to say self.hash equals hashlib.sha256. We have to reset. And now we have to update again, h.update. And we can just copy and paste this. There we go. Okay. So while our hash is too big, essentially, while it is bigger than our difficulty requirement is going to allow, we're just going to increment the nonce by 1. We're going to reset the hash, and we are going to redo the hash. Remember that the reason we reset it is that, as we saw here, it is a cumulative operation. So as we pass in more data, the changes kind of stack on top of each other, and we need it to be hashed in a one-time instance. And also, yeah, well, that's the only reason. It's a cumulative process, so we want it to work like that. Okay, so this is going to mine a block for us. So when we create a block, so let's go over to our main function. Instead of that, we're going to and say from block import block. Okay, and let's say we're going to create a block. We're just going to call it block. We're going to instantiate it here. And here we're going to pass in our data. So I'm going to type in hello world. Oh boy, why? And now we can say block.mine. And we're going to give it a difficulty of 10. And then we can say print block.hash.hex digest. And that should give us exactly what we're looking for. So if I clear the terminal here, and I say Python 3 main.py, we have an issue. H is not defined. Block.py line 10 in mine. 10 h.updates self dot hash.update. Aha, there it is. I see it. Don't think you can pull the wool over my eyes. Hash.update. I saw that. Okay. There it is again. Problem with working at a terminal sometimes. Anyway, okay, I think that's all of them. So now we should be able to clear that. There we go. Okay, so we have a hash of our block. Now we can also print out, let's see, we're going to print the hex digest, and we're going to print block.nonce, and then we're going to print block.data. And what you're going to see is that we are going to increment the nonce 192 times. So this took 192 iterations to solve, but the data itself can remain preserved in the block, and we still get our hash. So this is essentially the amount of work that is done to hash a particular block. But there's more to doing this. So first of all, I think we need a more difficult block. So let's put in 20 here. So see, now it's taking some time. Okay, and that time is work done. Okay, that's kind of what gives a blockchain value. So I haven't spoken about cryptocurrency yet, but sort of the first part of the value that is generated from a blockchain comes from the fact that your computer has to do some work in order to mine something. So I had to test, what is this, 816,451 different hashes, different nonces, in order to find one that, when paired with my data, gave us a hash that was less than our difficulty requirement. So that is the work done. That's the first part of the value generated in the blockchain. But there's more to it. Okay, so before we go any further, what we have here is essentially the individual item. So if you remember my reference to the linked list, this is essentially the node in the linked list. But we also have typically when we are implementing a linked list, we're going to have two separate objects. The first one is going to be the nodes containing data. And the second one is going to be this secondary object that is designed to traverse the list and allow you to perform operations on the list rather than on the node. So we're going to create a new object called chain. Okay, we're going to create a class chain. We're going to def init self. And let's say that we specify our difficulty at the level of the chain. So when we create an instance of a chain, we are going to right then and there say, how difficult is this chain going to be to mine? Now, you might not necessarily do this in every instance of a blockchain, but let's just do that here for simplicity. Okay, so that's our difficulty requirement. We'll say self.difficulty equals difficulty. We'll tie that parameter to the object itself. And we're also going to need a list that can store our blocks. So we can just define that as self.blockchain or blocks. Let's say blocks equals an empty list. Okay, and then as we mine blocks, we are going to add them to this list. Okay, but we also kind of want something for data. So we're going to say self.pool. We're going to also set that equal to an empty list. So what's going to happen is that these blocks are going to be created out of the data that comes into the pool. So let's say I type in a message like hello world. Then that message gets added to this pool. This is kind of the lobby, the waiting area. You're waiting for someone to come along and mine your data into the blockchain. So then all of these other nodes are going to be checking the pool and seeing if there's data in it. If there is, they are going to grab that data and mine it. They're going to use the mining operation on that block. Once they solve the puzzle, they will send it back to the chain. The chain will then test their result and make sure that the result suits the difficulty requirement. It will then add it to the list of blocks, and that's how it will work. Okay, so first thing we're going to need is something that receives a block and tests it. So we'll call this proof of work. It's going to receive self, and it's going to receive block from the outside, the outside world. Anyway, so what we're going to do is basically return whether or not the resulting hash from the block we're sent matches the difficulty requirement and what the block says its own hash is. Okay, so return. Well, first let's actually say h hash equals, what is it going to be? We're going to need hashlib again here. So we're going to set hash equal to SHA-256. We can then say h.update and then string version block code 2tf8. Okay, so that's going to give us the hash that we get. So when we test the block, what do we get? And now we can say, okay, what are they saying they got? And are either of these actually less than the difficulty requirement? So this is pretty cool to watch. Thank you, Dwayne. Thank you. I appreciate that. Good man. Anyway, so let's return. So this is going to be return block.h.hexDigest equals h.hexDigest. So we are going to make sure that this block's hash equals what we just generated. So make sure that they have done that part correctly. But we also want to make sure that h.hexDigest as an integer. So we need to cast that as an integer. So int h.hexDigest base 16 is less than 2. to the 256th power minus self.difficulty. That will tell us that the block has successfully been created and it has been mined appropriately. Okay, so now we are going to want to add the block to the chain. So we're going to define add to chain self block. So we are going to first, we've received this block from someone, some node has sent us this block. So we are going to first test it. So if proof of work block, then self.block.append block. Okay. Now, so what's happening? We start off when we first create an instance of our chain. We're going to specify that it has a certain difficulty to it. Then we're going to create an empty list of blocks, and then we're going to create an empty list of incoming data. And someone's going to submit a block to us. And what we're going to do is test that their block satisfies all of our requirements for the chain. And if it does, we're going to add it to our list of blocks. Okay, it'll just be added to the end. But we are missing something here. Okay, if that were the case, if that was all that we were doing, then anybody could come in later and just remove one of those blocks or change one of those blocks. Okay, that would be easy to do. And so the security in a blockchain comes from this next step. And this step is going to be linking these blocks together. So let's return to our block object here. So instead of just having my hash, I'm going to have my previous hash. Okay, so when I create my block, we're going to pass in a previous block. And we're going to say my previous hash equals previous block dot hash dot hex digest. Well, let's just say it equals previous block dot hash. That way we have a reference to that entire object. So now we have linked these blocks together. And let's include this in our own hash. So we're going to pass in self.previous hash data and nonce. So first we pass in the hash that was generated from the previous block in the chain. Then we are going to pass in the data that we want added to the chain. And then we are going to pass in the nonce that we created or that we currently have for our block. Okay, and this links them together. Okay? So let's go to chain, and we need to add another requirement to our proof of work. So in addition to making sure all of that is true, we want to make sure that and the block that they're sending us, that hash equals, or not their hash, I'm sorry, their previous hash equals blocks -1, our previous block, what we think is the previous block, dot hash. Make sure those two things equal one another, because we want to confirm that the thing that they have sent us is in fact the next thing in the chain we are actually trying to build, and not just some rogue block that happens to satisfy our difficulty requirement. A rogue block, I like that. Anyway, so if it indeed satisfies all of those requirements, then we add it to the chain. And think about the effect that this has on the blockchain as a whole. Okay, remember that our hashes they're unpredictable. Okay, we can't, the fastest way to find out what the hash of any particular data is to generate the hash. And we have created a system in which we have essentially eliminated a certain number of hashes as being viable. Okay, this creates a lot of computational work for our machine. Okay, so it takes some amount of work for us to generate the hash for any particular block. And once we do that, then we are actually going to link our block to other blocks in the chain. So let's say my block is here, and my block references block A, which is linked to by block B, which is previous block C. It goes all the way down. So this is the newest, and this is the oldest. Okay, if someone wants to come in and change this one, that would require changing the nonce and hash of this block. But this block's hash is stored in this block, so they'd have to change this block as well. Remember, their hash would change completely, and this one, and this one, and it will just keep cascading. And if you think about the difficulty that we've imposed on this, that becomes inviable. So if I want to change 100 blocks, but it takes an hour to mine every single block, then it's just infeasible. So, and in that hour, if a new block is added, I have more work to do. So I have to be faster than the chain itself. So it becomes infeasible to actually manipulate the past in a blockchain. Brooks should be self.block -1. Good eye, sir. Good eye. Okay. And I'm curious to see if this actually works. I know what I'm doing, trust me. But I'm curious. Sorry, I bumped the mic. Just doing a raw equals like this. I don't know what it's going to test. It's going to test to see if those are the same objects, I assume. And I don't know if the SHA-256 algorithm has overridden this equals operator. So we'll see what happens there. I might need to do something a bit fancy, or I could just convert it to an integer and see if those two integers match. But let's test the objects and see what happens. Okay, so we are going to add this object to the chain if it works. Okay, so now we want to be able to add some data to the pool. So def add to pool. Gonna be easy. Simple enough. Just add the data we want. We'll just assume it's a string for the most part. And what else do we want? We want mine. Okay, so when we call the mine function, we are going to test if there's anything in the pool. So if len len? Yeah, I think it's len of self dot pool if greater than 0. Then what we're going to do is pull the first item out and mine it. So self dot pool. Well, we're going to need to create a new block for it. So data is going to be equal to self.pool and 0. We're just going to take 0, so we can say pool.pop. And that's just going to pull the first item out and actually remove it from the pool, so it's no longer there. So now we can say, okay, so we have removed that first item and we are calling it data now. So we are going to create a block for data. So let's import blocks. Well, okay. So here we are just assuming that the raw data is in pool, not an actual block. So we are going to create a block. So we are going to say block equals block. And what do we need to pass into it? We need to pass in the data and the previous block. So we're going to pass in data, which we've already pulled out there, and self.blocks -1. Okay, so we pass that in to create our new block object, and then we are going to say block.mine, and we need to pass it what? We need to pass it its difficulty, which is just going to be self.difficulty. And then once we have done that, we are going to add to chain block. And I need to be putting self dot. Yes, okay, self dot add to chain. And if self dot proof of work, so let's go to this hash proof of work. Yes, I think that is going to work. Okay, so the only thing left now is how do we start this whole process? So if we look at this, then in order to start it, we need to add something into the pool of data. So what we're going to do is over here, rather than creating this from chain, import chain. Dang it. Okay. And what do we need to pass into the constructor? Just the difficulty. So let's say chain equals chain, and let's give it a difficulty of 20, just to give it a modest time frame. You'll see why in a moment. Okay, so now we want to enter an infinite loop just so that we can keep watching this happen, because it's kind of fun, honestly. But we're going to enter an infinite loop. So while true, we are going to say first data equals input add something to the chain. Okay, so you're going to type something in, and then we're going to say chain dot add to pool. Pass it. Remember that this is going to just append it to this list. Then we can call the chain.mine function. We're going to see that there is something in self.pool that will take that out of the pool. We'll create a block out of that thing, and it will mine it, and then we'll add it to the chain. Okay, so we can say we've added that to the pool. Now we can just say chain.mine. But there's a problem. Okay, before we do this, notice that we are setting the block equal to self.blocks -1. Okay, so we say that the previous block equals this, but we don't have anything in here to begin with. So if we specify -1, then that's going to be an index out of bounds because there is nothing in our initialization. Let's go ahead and create the first block in the chain. So I'm going to create a new function called create origin block. It's going to be passed self. Here we are just going to create a block that basically has no data in it. So let's say origin equals block. And what do we need? Data in the previous block. And so that's what the trick is. How are we going to put a previous block in there? Well, we pass none, I think that I don't think that'll work. See, if we always have to pass in the previous block, then there's no way to really create one of these, is there? That's rather circular. But so instead of that, let's just pass in the previous hash. Okay, that'll be easier. We need to do a digest here. And I need to lose the face cam because the battery is running low. So I'll come back on with my beautiful face in a little while. So, plug in the okay. So I needed to do a hex digest there, and is there anything else that I need to look out for? I don't think so. Okay. After I create a block dot hash. There we go. That's what I needed. Okay. So let's see. We're going to create that. Our origin block is going to have its data is going to be nothing. So its data is going to be, let's just send it origin as text. That'll be its data. And the previous hash, we're just going to create a hash object. So 256. And let's just, I don't know, can I do just an update? I have to pass it some data? No, I have to pass it some, so. Whoa. Can I pass it nothing as that data? Will that work? There we go, that'll work. Okay, so that will be our previous hash. So our previous hash is going to be H. We're going to create our thing. So we can say origin.mine and self difficulty. So we will mine the first block ourselves. And then see, we can't actually call this thing for the proof of work because if we do that, then it's going to test our previous block -1. So we're just going to kind of manually insert this into the blocks list. So we'll kind of go through the back door there. It's a little cheaty, but that's okay. Okay. So we'll go ahead and mine it. We'll be truthful about it, and then we'll just say self.blocks.append origin. Very beginning here. Once we initialize it, create origin block. Okay. So go into this infinite loop. We're going to add data to the pool. And then we are going to mine that data. And that's pretty much the whole process. And let's see. Let's create a little iterator here. Let's create I. Set it equal to 0. And let's say end of each loop, we're going to increment I by 1. But before that, say if I divided by 5, 0, we're going to print chain dot blocks I. Probably should be I minus 1, should it? No, I think that should work. So yeah, every 5 blocks, let's just print out the block and see what it looks like. And that should do it for us. So let's go ahead and clear this. Python 3 main pi. The origin block is not fine because I need to write self. One part where we find all of my typos. Chain. Ah, see, it's mining in between these. That's why it's taking a little bit. And it didn't like it, unfortunately. Okay, in proof of work, h.update. H is not defined. Okay. Here. It is definitely just stuck with one variable name. Block.hash. Sure it is. I should have just changed the one where it said hash to h, and that would have that would have solved it. But so the reason it takes a second here is that it first starts by mining that origin block. So we're actually mining the origin block. Now it gives us the opportunity to add something to the chain. So we can world. Now it's going to mine hello world. Ah, chain has no attribute block. Where is this? Okay, in proof of work, self.blocks -1. I think Brooks, you pointed that out. I thought you were talking about something else there, but apparently you were trying to stop me. I tried. I'm sorry. Anyway, try this again. We mine the origin block. We mine hello world. There we go. Oh, okay. Okay, so what did it print out there? It printed out the, if we look at a block, printed out the previous hash, so that is the hash of the origin block. Printed out the data that's stored in the origin block. Or, yeah, this is, oh, so this is all for the origin block. Okay. Yeah. So this is the origin block. This is the nonce for the origin block. This is the data origin that we passed in, and this is the previous hash that we sort of hacked together for the origin block. We don't really have a previous hash for it. We just kind of stuck that in there. Okay? So now we can add more stuff to the chain. So subscribe. Got to throw it in there somewhere. There we go. Okay, so now we're going to have to add a few more things to the chain, and then it'll eventually print out another block. So let's see. I don't know. Shoes. I don't know. Throw in the chat. What should I mine into our chain? Throw it in the chat. If I see something good, I'll add it in there. I'm gonna add my name. I think the next one should be printed. Taking a long time to mine my name. There we go. Good. You guys aren't giving me anything in the chat to mine. You're letting me down here. Okay, so let's just do ABC. I don't know if you can hear it, but my computer, you can really hear the effect of mining on it. I'm going to pick it up, and I don't know if you can hear it. So that is the work that my computer is doing. And there we go. So this is our previous hash. There's our data. And this is our nonce. So that's our working blockchain. So we actually have managed to get this up and running. We are actually adding things to a chain. We are hashing them. They have a difficulty associated with them. And yeah, it's completely working. Now, there are some reasons why this is not actually... Oh, before I do anything, I pitched the whole Git repository. I didn't push it out to you guys at all. So let's do that. So what? Ooh. Okay, we're going to call this message going to be oh, we're almost there. Because I have a virtual environment of Python in this Git repository. That probably wasn't wise. Anyway, okay, so now you should be able to visit GitHub and check out the sketchbook. Let's refresh it. Link to this is in the description. Here's all of the code that you need for this blockchain. So you can look at this, you can copy it, you can do whatever you want with this file. If you don't mind, go ahead and leave a star and go ahead and follow me on GitHub if you're interested in this sort of thing, because I do a lot of these kind of tutorials, and this sketchbook is where I'll be experimenting a lot. And yeah, okay. So I am going to take a quick break here, grab some water, and I will be right back. And what we are going to do is talk about what this is missing and what you would want to do to bring things further and make it a little bit better. So I'm going to leave you here for a moment, and I will be back shortly. Okay, welcome back, ladies and germs. How are we doing on battery? Back yet? Not even close. 17%. Oh boy. Okay. Before we go any further here, I would actually really like to demo this a little bit better. I want to print it a little nicer so that we can have a better visualization of what these blocks actually look like. So after each one, I'm just going to go ahead and print every single block. So instead of doing this, in the chain, let's go ahead and once we have added it to the chain, we're going to print. Okay, well, let's say we're going to print it in a nice way. So print block.hash.hex digest. And let's add some labels. Previous hash. And let's put a \t to give everything some nice. I want you guys to be able to see what these blocks actually look like so you can kind of visualize the linking of them. Previous hex. What's next? What else do we need? Hunts. block.nonce and print data data. Okay. And when I create the origin block, I find the block. Oh, okay, I see. Yeah, so it will print it when it's done. Okay. We'll print all of that. And let's add a few more things just to make it look nice. Go. And that. One more. Great. So let's run this. And in main, I actually just want to say, I want to do a little different for I in. Let's do 5 blocks. We only need 5. And we'll just have our data be the number that we are passing in, okay? So this is just going to generate 5 blocks for us. So we can run main.py. Going to create the origin block. Uh-oh. I want the input. No more input. We don't ask the user for input anymore. Okay, we mine the origin block. It does take a minute. I wonder if there's sometimes I can't tell if it's there we go. We got it. Okay, so this is just going to keep generating some blocks for us. And what we can see here is our data is 0. So this, well, it didn't print out the origin block, which is a shame, but that's okay. We have one too many tabs here for previous hash, but let's take a look at this one. So the hash of this block is this, and the previous hash is this, and the hash of this block, you can see the B7A87, B7A87. We can see that that's how we are linking them, and we are requiring different nonces for each one. And the nonce correlates to the number of iterations in the mining loop that we need in order to generate this new hash, and we can just keep linking them together like this. So this is our working blockchain. How would we use this in a real world scenario? Well, one example I thought of is you could set one of these up on, say, a Raspberry Pi, and to be clear what I'm talking about here, I mean this code that I have written right here. What could you use this code for? You could set one of these up on a Raspberry Pi and then say, make a trading card game with your friends or your family. Or you, like if you have kids, you could take this blockchain and make it some way of logging their chores. So like, you put in chores into the, into the pool, and then your children would mine the chores out of the pool by using some sort of timer that would say how long it took them to do it, or whatever it is that they do. And you could create a blockchain using this code to do something like that, something on a small scale that would work. But unfortunately, there are some problems with this. So the first problem, if you see any problems with it, by the way, throw it out in the chat. If you think of a problem with this implementation that's not going to work, then say it in the chat and we'll talk about it. So the first problem is Python. Unfortunately, Python, it's really easy to make something like this. You can see how in 3 files with, I mean, one file is 7 lines of code, and these are not extraordinarily complex files. We're able to actually create a blockchain. But unfortunately, the way Python runs makes this extraordinarily slow. So the way that Python works is that we have basically, let's create a, how do you do? I think that's a long comment. Anyway, it doesn't matter. Anyway, so we think about our computer and we think about this layer right here. This is the base layer hardware. And then we have our processor on top of it. Okay, your processor is what is running all of the different applications on your computer. So, like, here's your operating system, here is Xcode, here is whatever, some game I'm playing, and here is the program I'm running. Okay, well, unfortunately, the program I'm running is actually the Python interpreter here. So I have my hardware. One of those pieces of hardware is the processor. Top of the processor, I run my operating system, which is then taking this Python interpreter, and on top of the Python interpreter, I then have the code that I have actually written here. What this all adds up to is extra CPU cycles. So I have to take a CPU cycle to get my operating system instruction. Then the next one I can take my Python interpreter. Then the next one I can take my program. And I have to keep going back. So I lose CPU cycles in this. And so Python is just going to be quite slow. And there's just a lot of things that it does for you. So here, I don't declare this as having any kind of data type. I just declare chain. I could say chain is 5 next. So Python actually has to go and look up what chain's data type is, and that takes time. So this is going to be slow. And when it comes to something like mining that is time sensitive, something that runs slowly is not an effective way to do it. Mr. Gamer, you could use Cython to speed up Python. Indeed, you could. I don't know much about Cython. I have not used it myself. And basically, it allows you to do some things like declare data types. And actually, I don't know if I am thinking of Cython the same way you are, but Cython is just the source code of Python. So in fact, we can import certain parts of the Python library into a C standard environment. So say I wanted Python's hashlib, I could just import their hashlib and use it exactly the same. But unfortunately, there's another problem that we need to deal with in our blocks here, and that is memory. So look at how I have to hash my block. Okay, when I want to hash my block, I have to create a string, and this string I will put in these fields in a particular order. Okay, and then that is going to be encoded in UTF-8 bytes. That encoding is what's passed into the hash algorithm. Okay, and so everybody on the network is going to need to know that that is what we are doing. We're creating a string that has these fields in this order, this format, encoded in this way, and we are going to update our hash with that result. And that is a lot. That is a lot of steps in order to get our data to a hash. And the reason we need to do this has to do with memory. So I create a Andrew, I gotta go. I'll check the rest later. Thank you for great content. Thank you for joining me, Andrew. Glad you were here. I hope you subscribe to the channel, and also check out our Discord. I'd love to talk to you more about maybe some projects you're working on, projects I'm working on. Love to get more in touch with you. So thanks for joining us. Anyway, so let's say that these are the memory addresses in your machine. And what's going to happen is that Python is going to decide how the bytes that make up an instance of this object are arranged. So maybe our hash is stored here, and then maybe our nunts stored here, and then maybe our difficulty is stored here. Oh, but we also need to store room for all of these functions, which are also part of the object, and they're in this too. So now there may not be space in between them. They may be continuous memory locations, but we are also including these functions, the memory for these functions. We're also including all sorts of different things like this. And the whole point is that nobody can look at this unless you, I guess, perhaps one of the people who originally wrote the Python programming language Maybe one of those people could look at this and tell me what this block looks like in memory, but I cannot tell you what this looks like in memory. As a result, I need to format it so that I do know what it looks like. And that's why I have to do this whole thing with the string method. Okay, an alternative is in C. So in C, if I define a struct and I say that this struct has an integer and then it has a character and then it has another integer, it's going to allocate 4 bytes and then 1 byte and then 4 bytes, exactly in that order. So we'll do those 4, well, those 4, that one, and then you'll have to forgive me for being precise here, but you get the point. So we'll allocate all of these contiguous memory locations. Then we can just take this entire stream of bytes and pass the raw bytes into our hash algorithm. This allows us to store it on our computer in a way that reflects exactly what we are hashing. So when I send this, exactly these bytes to you, all you have to do is hash them. You don't need to format them. You don't need to parse them. All you need to do is hash them and see that they work. And then you can also apply the same template to it. You've gotten, what is this going to be? 9 bytes here. So the first 4, you can just assume they're an integer. And then you can assume a character and then another integer. We know the format. We know that skeleton. But our raw bytes, we can just pass this into the hash and we can just pass it back and forth to each other. Python doesn't allow us to define it in this way. So in that sense, this is a little bit not up to the task. Camel Trader. I'd like to recommend libsodium for crypto stuff like hashing in C. Yeah, when we get to doing this in C, hashing is going to be an interesting task. So if we come over to my sketchbook, we can actually see, I'll veer off task for a bit here. Why not? Yeah, here we go. I was experimenting with this using OpenSSL, and if we look down here, we can see how I did the hashes in OpenSSL. It's actually quite similar. We basically create a digest and we update it. Now, I want to know SHA-256, or actually just hashing algorithms in general, that I understand why both OpenSSL and HashLib do this. Maybe HashLib is dependent on OpenSSL, I don't know. But why do they do it as this cumulative update? I would like to know, because I would kind of like to create my own SHA-256, because OpenSSL is not very lightweight, and I think we can do our own thing. Camel Trader, we still need to be careful with structure padding, though. Can you be more specific about what you mean by structure padding? So yeah, I was trying OpenSSL here. I don't really love using third-party libraries, but this is one of those ones where creating a SHA-256 algorithm from scratch, it's something that we can do. It's something I actually really want to do, but it's something that is it's going to end up taking a lot of time, and if we spend that time on SHA-256, we're not spending that time on getting our peer-to-peer network and blockchain up and running. So I think for now we'll cross that bridge when we get there. Anyway, okay, so Python does not allow us to define how this is stored in raw memory. Okay, C will allow us to store things in a particular way in raw memory. Camel Trader, libsodium is pretty lightweight. You could probably look at the source code for inspiration. That would be fantastic. I'd love a link. Anyway, so yeah, Python's not going to allow us to define how our memory is stored like this, so our hashing requires some formatting. And that's something that, while it's not extremely difficult to do, it is a bit of a pain. Now, why don't we... I've been wanting to try something. This is something I've been working with in C. Let's just run a little experiment here. I want to... Let's see. Okay, so I'm going to create a file. We're going to open a file on my desktop. Test.chain. Okay. And now I want to f.write. Can I just write my chain to this as some bytes object? Okay. And now let's open it again. So f equals this. Open it in read mode now. And we're going to say c equals f.read f. Oh, dot read. Okay, there we go. Give us our raw bytes. And we could say f.close again. And I want to print c dot difficulty. Let's see if we can just get it to tell me what the difficulty of this was. And let's just make this, I don't care about mining it this time. So it is pretty cool to watch it mine itself. But it's going to mine the origin block, that's fine. Must be a string, not chain. See, that's the thing, is I can't even, in Python, I can't save my objects as a bytes file. I can't save the, well, I mean, maybe I can. Maybe there's a way to do it. But in C, it's really easy to just take the struct that you have and write it to a bytes file, a binary file. And that's something that's not as simple in Python. So if we want to take this, look at this. See this pool and blocks. This is an array. This is stored in volatile memory. So our machine needs to remain on, and it needs to be uninterrupted. It will, and this list is only ever going to grow. Remember, our blockchain is immutable. So this list only gets bigger and bigger and bigger over time. So it's completely limited by the amount of RAM that we have. It's volatile to fluctuations in power availability. So there's a lot of problems with storing this in volatile memory. So we would want to store it in on the hard drive somewhere. But if we store it like that, we would need to do something like this, where we create some formatting, and we would store this formatting, and then when we're ready to load it again, we would load it and unformat it back into one of these blocks and recreate a block. It's just a mess. Whereas in C, for example, we could just take whatever the raw bytes are of this and just take that pattern, stick it in a file, and then load it back in later. So it becomes really easy. Python isn't really equipped for that. Storing this all in volatile memory isn't really going to work. Also, we have a pool for work, but I mean, the blatantly obvious thing that makes this not suitable for production is that it is not using any networking. So you would need to create a peer-to-peer network in order to run this on. We've got that going over on other parts of the live stream, but nothing here has any networking. So you would need something like that. You could, for instance, use Flask, the web framework Flask, and put all this into a Flask environment and do something on a website with this mining, and that would solve the problem. But yeah, this has no networking in and of itself. It's just the chain part, the blockchain. Okay. Camel Trader. And Mr. Gamer says use Python. Use Python for what exactly? And Camel Trader. Structure padding is that you can't just hash the bytes of a struct, because the compiler is free to insert padding bits to make sure that the members are fine. Structure padding is that you can't just handle the bytes of a struct. You can't just hash the bytes of a struct, because the compiler is free to insert padding bits. So in my experiments, I don't know, maybe you're looking at one of these and you're referring to something that I did. So if you'd have two instances of a struct and all of their members have the same value, pairing them with memcopy would still say they aren't the same. So you're saying that in between, so a struct is not necessarily, if I'm understanding you correctly, what you're saying is that if this is our struct and we have our, okay, and if we define a struct that has a character, then integer, not necessarily going to be all contiguous memory locations. It might, the compiler might skip one. Is that what you're saying? I'll come back to that in a moment. Compare. I'm not quite sure what. So if you're saying that the compiler will put things in between, like they'll just insert a space in here so that this might span a total of 6 bytes instead of 5, then that becomes a problem for us. Unless later we can load it in and it will align itself. Now, that being said, I did run some tests with this. So let's go ahead and get out of that virtual environment. And actually, so where did I run tests with this? So over here, I have in this a block.h. So here's my header file. What I do is, oh, is this an old one, I think. Let's see, hold on. Which one was it? I think that my GitHub one missing a. No, no, well. Anyway, let me just show you what I was doing here. So this is the client function in the peer-to-peer network, and what I do is I create a struct of block headers, and I fill in all of the parts that I need, and then I just create a void pointer, and that void pointer is the data of the block, and it is the headers that I put in here, and it just sticks them all together in contiguous memory and then sends that to the server. Server, which is defined up here, retrieves those and just casts those raw bytes back as block headers. It can then read all of the different parts of block headers. So it seems like just laying over top of these raw bytes my block header struct that without fail gave me a clean thing. So by the same principle, I should be able to just write this struct to a file, no problem. So I've tried this by sending it over a network, but I'm interested to try it with saving it to files. And I think whatever happens, I think that we kind of have to go the route of using these raw bytes because it's just a much cleaner way to do it. So let's, whoops. Okay, let it catch up here. Falling behind a bit, I think. Oh, no, it's good, it's good. I think this one is. Struggling a bit. There we go. Okay. So yeah, we do have some problems with speed just because of the nature of this being Python. This whole thing is not in a networking setting, and we have some problems with how we are going to store this in memory. But I think the big takeaway here isn't that this is the functional blockchain. Good morning, Joseph. This isn't the functional blockchain. This is just a demo to show you how a blockchain works so that everybody is on the same page with what these are actually doing and how this is all working in principle. So we have essentially, fundamentally, we have this block, and the block has a hash, a previous hash that links it to the other blocks in the chain, or the previous block in the chain, has a nonce, which is just a field that we are able to manipulate in order to get this resulting hash to be below a certain difficulty requirement that is specified by the chain later. And inside our block, we are going to put some kind of data. Now, for now, we have only put some strings into this data, but in the future, we'll put other kinds of data into it. And in the C version of this, what we are working on doing is, if we look at the .c file here, what we are doing is essentially putting any kind of data we want into this. So we have, maybe you're sending a JSON string, or maybe you're saving, I could save this video, this live stream, I could save that as the data in my blockchain. So whatever data someone has is here. And then the process of mining has to do with the difficulty established by the chain. We are just going to keep generating hashes over the data and previous hash and nonce until our incrementation of the nonce generates a hash pretty much by random that is less than this difficulty requirement. And once we have that, it gets added to the chain, which essentially is going to link all of these items together and make it so that the more items you put behind a block, the less likely it is that it will be changed, because you'd have to change all of the subsequent ones, and the difficulty of doing so makes that impractical. So that is sort of our overview for the chain. So camel trader, unsigned long needs to be 8 bytes a line, so the compiler inserts 6 padding bytes into after unsigned car. So size of t equals 16. Bytes inside t are together only 8 plus 1 equals 9 bytes. I'm going to need to read that when I am not live streaming, because I am not going to come up with a sensible response to that at this very moment. So, with an audience waiting on my words. So, saving that for later. We'll come back to that. Okay. So let me give you a view of what we are going to be doing here in the future. So now that we have an understanding of these blocks, we kind of need to get into the nitty-gritty of how these things work. So if you wanted a fully functional blockchain out of this particular video, fortunately, we have something that could be slightly modified for it, but it's not going to actually be a production thing. We are working on the production version over here in C. So let's pull that up, and let's just take a look at some of the problems that we are facing in C. So this is a much cleaner version of our client-server function. And what I'm working on right now is, sorry, getting messages. I had do not disturb on, but someone has penetrated that barrier. Someone. Anyway, okay, so currently the problems we're facing here are in developing the block. So I'm going to get status. Going to, what did I name it? This. Okay, there we go. So here I'm working on something kind of interesting. So I've copied over the client and server. No, I haven't. What is this? So this is demonstrating how we can save a block in contiguous memory spaces. What I do is create two separate structs, and these have a lot of the same characters. We're not going to be able to see our Python and C side by side, unfortunately, but that's okay. And I create all of these fields. So an unsigned character for the previous hash of 64 bytes, and then an 8-byte unsigned long for the nonce. The fingerprint, that is identifying who created it, timestamp. I have some additional fields in here, but don't worry about it. These are just some additional metadata points that I want to collect. So we create this headers struct, and then we embed that within another struct that is a block. And the block is it has the block headers embedded in it, so that will be all contiguous memory starting the block. And then afterwards, we allocate a single byte. And then what we're going to do is when we are ready to actually put the data into it, we can say, where do we do that here? Oh, okay. So in this case, I decided the data was going to be a transaction. And don't worry about the structure of the transaction just yet. I'll show you that in a second. But essentially what I do is I take the address of that single byte that we allocated for the block's data, I cast it as a void pointer, and then I say that that struct is a transaction, even though it's only 1 byte. And the reason for it is that what I have done is allocated enough space. Where is it? I made this a few days ago, so yeah, right here. So when I malloc for my block, I allocate enough space for the entire block plus a transaction, because I know a transaction is coming in here. So even though my block only says that there's a 1 byte field, we just have 1 byte and then all these extra blank spaces at the end. And what I do is use string copy. No, not there. Right here. I just cast my block's data as a transaction pointer, and then I can just access those fields, and each one lets me do it. So what this program does is we create an instance of a block, and we set those parameters that are embedded within it, the fingerprint, previous hash, blah, 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 all of that. And then we print out all of those things and return. That's right. So we're just kind of demonstrating saving this all in contiguous memory. If I run this, build failed, of course. Wrong. Oh. Sorry about that. Sometimes it takes a second to run, especially when I'm doing all this other stuff. Camel Trader. Yep, the block used there, hashing, it would use the raw bytes, wouldn't work. You need either hash the members manually or use a compiler extension like attribute pack. Okay, we're going to have to talk about that. Here we go. We got something interesting here. So here we get something very similar. I think it's still trying. We got a fingerprint, a previous hash, the size of the block, its nonce, and a timestamp. And this isn't actually hashing anything. This is just demonstrating that we can save everything together. But Camel Trader is arguing that that's not going to work. So if you're not already, I think you are, but are you on Discord with me, Camel Trader? If you're not, please join me over there, because I would like to discuss that with you this week, because I'm trying to finalize this design. It seems like it would work, and I think somewhere you're saying it wouldn't, but I feel like somewhere I did in fact do that. Can you tell me why exactly would there be padding? Well, anyway, you and I will talk about this later. Essentially what I found is that I can create a example of a transaction by doing the same thing. So by default on the network, I can define structs in this same way where I create headers and then a single byte for data. Then I can just reference that data as its address and cast it as whatever I want. In this case, I think I cast it as a number. But that's sort of the problems that we're facing. And the point of this is to make something that's a little bit more robust than a Python version can be. And that's just due to the nature of Python. So I think that'll kind of wrap it up for now. Let's see how the battery is doing. I'm going to turn my face cam back on. It's not going to last very long, but I'll turn the face cam back on and we'll do a little Q&A if you guys got any questions for me. Let's see. I'm going to this, and any moment now, I should be back. Okay. Well, yeah, there I am. Okay, great. So, I think the link was removed. I have a link. Well, you can join me on Discord, and we can discuss it more there, because the point for this week was just to get everybody on the same page as to what a blockchain even is. So, trying to get these things to be in contiguous memory, I know there's a way to do it. There absolutely has to be a way, and I'm not sure exactly. Okay, well, here's a question for you. It's supposed to be a Q&A for me, but I have a question for you, Camel Trader. So when I am allocating my bytes, so right here, when I create my block, I create it to be exactly the size required for a block and exactly the size required for a transaction. Now, the exact size required for my block header is 64, 64, 20, 8, and 8, so that's 164. So I get exactly 164 bytes for this. So I don't know how there can be any padding in there. And if I just pass those 64 bytes into SHA-256, I feel like that should work. So I'm not entirely sure. But that's all I'm seeing for now. And yeah, let's see if maybe there's some questions on Discord we can answer, or even on, oh, look at that. I see it. Okay. Yes, let's go. Oh. Interesting. Okay. Okay, right here, mem compare. And mem compare, let me look up mem compare. Compares the first n bytes of memory area. First bytes of that, okay. Is this a problem specifically? Is this a problem specifically because of unsigned long, or is it to do with structs and the way structs are allocated in memory? What is the cause of this? Because again, what I keep seeing, again, here's another question: is it relevant that these are all defined on the stack? So pretty much every instance where I utilize my blocks, I'm defining things on the heap, right? So I am defining exactly how big something is. So I can see that maybe if they're doing it in the stack, where the processor is defining how big something is, then that would happen. But when I'm doing it manually on the heap, I think that I'm getting exactly the number of bytes that I need. Because Like if I were to, where? Down here. Like let's say I save this to a file. And let's go ahead and, where is it? Oh, I'm in the wrong thing. No wonder. Okay, so if I take this, create transaction block, and if I just write it to a file. So let's do it up here. Write file. I created this function in my library earlier. Very glad I did. Users Eric slash transaction.block. Okay. If I run this, oh, we're getting my libom here. Use makefile. Sorry. Work? No. Where do I define that? Systems, files, .h, include files, makefile. Systems, we have files.c, files.o. Oh, it's right there. It is right there. Maybe I need to include it manually. Oh. Xcode has an interesting thing with the way it's looking for these libraries, where it like wants me to change the name of it for some reason. And there we go. Okay, great. So I've just saved a bytes object to a file. And if I load this in and cast it as my block object, it should still work. Do it how structs now. Sign long bytes. I don't see what the problem is there. I've sent another Discord message with a like demonstrating the size of a string. Do what you expect it to. Take a look. ASM generation compiler return 0, size of t. And does this have to do only with the unsigned long data type? Is that specifically what it is? Because I'm using an unsigned long in this block. I don't know if that's going to actually make a difference, but is it that specific data type, or is it general? I don't know. And what do you mean aligned to 8 blocks or 8 bytes? Because an unsigned character is 1 byte. So how can it become unaligned? I'm not sure exactly what that means, but maybe I just need to do some more research into that. So that's fine. Yeah. So we've loaded our block in, or sorry, we've been able to export our block. If I open it with text edit, what it'll say. Oh, that's interesting. Longer than it looks too. Anyway. So I could load this file back in, and if I do, okay, so here's kind of what we would do next is I would, if I save this to a file, what I can do over here on this, if I go to my desktop, then I can do draw some a 56. Do a SHA sum of that file, I get this hash. And you know, if I send this file to you, then you should get the same hash. And if I can load this file in and cast it as my block, then it should be working. And as long as I always use it in this circumstance where I'm casting a void pointer to as a pointer to one of my blocks and the data as a pointer to one of my transactions or whatever else is in it, then if the bytes work, then hashing the bytes gives you this, and I think we'll be able to understand each other. But that's going to be in the next steps. So you see, we've gotten on the same page now as to what the blockchain is, and I can just tell that, like, we at least understand each other. We know what the next problem is going to be. So I think that is going to suffice for today. Keep talking to me, Camel Trader. Join me on the Discord more. We'll talk more about how we're going to actually allocate memory for this. But for today, I think that we have done a good job getting our blockchain up and running and just having some fun with it. So thank you all very much for joining me. I am still on Discord. If you like this sort of content and you want to see more things like this, both in tutorials, developing this blockchain further, going into some programming, a lot of different kinds of projects, feel free to subscribe to the channel and like the video. So with that, thank you for joining me, and I will see you next time. Toodaloo.